Folks, so in the last lecture, we talked about the human hand, and you are all supposed to have watched this video from this medical class on the anatomy of the human hand, which is an incredible instrument with like 21 degrees of freedom. So today, what we are going to do is to learn a bit about how robot hands have been built. And people have been doing this for decades. But the most recent entry is the leap hand from our friends at CMU. So Kenny Shaw, Ananya, and Deepak. I mean, Deepak used to be a student at Berkeley. Okay, you've got their opening slide. And what they're going to do for the next half an hour is going to take us through the various choices in robotics hand design and their own solution for this. So with that, take it away.
All right. Thank you, Jitendra. So,
okay, so I think I should mute here.
Okay. Yeah. So let's dive in. So you guys already looked at the human hand, and like it has a lot of degrees of freedom. It's very suited for tool use and so on. And what we want to do is in robotics is to replicate this capability in like hardware. So what we'll talk about today is what are the design principles when you go about doing this. So there are broadly two categories we want to talk about. The first is kinematics. So how should we design the joints of the hand? In what positions should we place them such that we get maximum dexterity? And the second aspect is mechanics. So once we have this design, how do we actually build it reliably in hardware? What hardware components do we use? What designs do we use? So I'm going to talk about kinematics first, and then Kenny will go over the mechanics part of it. The most important part of the human hand is the opposable thumb. So if you look at the two major kinds of grasps, they're the power grasp and a precision grasp. And in both of these cases, for a successful grasp, you need to apply opposing forces on an object to get net zero force. And that's what makes that's how you can place the object stably in your hand. And the opposable thumb allows exactly this. It allows the application of force in opposition to the fingers. And without an opposable thumb, there's no way you can stably grasp these objects. How do we quantify thumb opposability? Let's say you have like 10 designs of robot hands and you want some way to compare these. How do you go about it? So one very useful heuristic is to look at the common volume that is reachable by both the thumb and each finger. So the larger the common workspace, the more the thumb opposability, because you can apply opposing forces in a larger space. So here's like a visualization. What you can do is you can sample points in the workspace of the hand and see if these points are reachable by both the thumb and each finger. So here we have workspaces for the pinky, for the middle finger, and the index finger. And of course, you can compute the volumes of these spaces. And the higher the volume, the better, like more use of the thumb you get. The second aspect is dexterity. So workspace doesn't provide the full picture. What you want is how dexterous the fingers are in various positions. So at each posture, how many directions you can move the fingers in. So let's look at a simplified finger. So here it's a finger with just two joints, and with some joint angles θ1, θ2, and some position x, y. Now what happens is that if you give each of these joints some velocity, you get some velocity of the end effector, and these are related by the Jacobian. So r dot, velocity of end effector, is the Jacobian times θ dot. Now what we want is to figure out what velocities can the end effector achieve for some set of θ dot. So let's say that you can, for some θ dot with the norm less than 1, what is the possible set of end effector velocities? And the larger this set, the more dexterity you have in this particular posture. So if you look at this theta dot less than 1 corresponds to a sphere in this space. And if you multiply it by Jacobian, this is a linear transform. So it stretches or squishes this space. So what this means is that this set corresponds to an ellipsoid. And you can compute the volume of this ellipsoid, which is proportional to the determinant of the Jacobian times the Jacobian transport. And these ellipsoids are called manipulability ellipsoids. So you can plot manipulability ellipsoids for fingers in different positions. And this is a very useful way to debug what is going on in your hand design. So for example, these are two different hand designs, and they differ by how the MCP joints are oriented. And we'll talk more about this later on in the presentation. But you can see how this impacts manipulability for the index finger in these particular locations. You can also plot the distribution of manipulability volumes across the workspace. So here, the intensity of the color at each point represents the volume of the ellipsoid at that particular point. And you can see that for the hand on the right, towards the middle of the palm, you get very little manipulability, whereas on the left, you get more manipulability. So this implies that the left design is better than the right one, at least as far as this dexterity metric is concerned. Okay, so these are like two principles that I talked about as far as kinematics is concerned. And then Kenny will talk more about the mechanical aspect.
Cool. Thanks, Ananya. Yeah, so I'll talk a little bit about joint and actuation design. So how do we actually create these robot hands to match these parameters and try to replicate the human hand in its functionality? So one of the most common designs you'll see out there, they'll use the motors directly as joints in the robot hand. So what that means, like you can see on the top right, these motors are basically chained together to form the joints of the hand themselves. So the servos like usually have motors and a gearbox and an angle sensor, and are just packaged together as each piece of the finger. And the output of the servo shaft directly drives the joints of the motors. And you'll see this in many hands. Leap hand does this, Allegro hand and D-Manus hand have commonly been used and use this design. The good news is this is very easy to produce. You take the servo motors, you chain them up, and you can control them very easily. However, the main problem is that strong motors are really big, which makes the robot hand really big. And if you use really small motors, they're typically very much too weak. And also the structure, the kinematic design, typically is dictated by the motor size. So you'll get like really bulky and boxy hands. And this is really, as you saw in the lecture, this is not how the human hand works. A lot of the strength of the human hand comes from our wrist and tendons. A lot of our actuation doesn't actually happen inside our hand itself, but the power is transferred up. So there's been a lot of work in mechanical space of trying to figure out how to transfer the power. And one of the most common ideas is a 4-bar linkage. And the idea is you have like 4 revolute joints, and you'll have one of them that's actuated by a motor and another one that's fixed in place. And you can see, in the gripper in the bottom right, if you do something like that, when you actuate it, the fingers will open and close. And you can define the motion at the end effector in a closed form way using forward kinematics. And you'll see like Inspire hand or Psionic hand will commonly use this design. And you see this in research a lot as well. And the nice thing about linkage design is it's very reliable and accurate. What the motor angle you get and the fingertip position is very easy to calculate. However, the linkages don't have that much compliance. And, when you smash the fingers on the table, sometimes the linkages will break or they'll slide off of each other. And these small components can be very brittle. And it's also hard to make linkage hands with many degrees of freedom. If you think about the Inspire hand or the Psionic hand, they typically have 5 or 6 degrees of freedom, which is far less, as Ananya said. The more degrees of freedom you have, the better manipulation you can do. And often these hands are very limited to only 5 or 6 degrees of freedom. So then, many people are looking at, well, how can we get more degrees of freedom into a small space? And tendon-driven hands have been very popular recently. What they do is you take a motor, you put it, usually into some part of the wrist or somewhere lower in the hand, and then you have these, fishing line or some sort of rope that is connected to the servo motor and connects up to the fingers themselves. So as you spin the motors, the tendons change in length, and it will change the finger and open or close it. This is sort of similar to how human tendons work in the sense that you have the actuation further away from the hand, and then you transfer it through some, a tendon. So once you make this tendon, well, then you have to actuate certain joints. And these joints are passive now, but they still have to be actuated. And there's different design choices on these joints. So one common one is a revolute joint. And as you can see, on the top right, you've seen the revolute joint a lot, in door hinges. It can rotate in one axis, and then every other axis is fixed. So it allows just a very simple rotation. And you would think this is the obvious choice of design. And you see many hands, this is the Dex hand, uses this. But the main problem is it's very brittle to out-of-axis forces. So if you take like a hinge and you try to bend it in different weird axes, like you bump a hand on a table, these joints will often break, or they're very brittle. If you think about your human hand, the fingers do, have a revolute joint in some sense, but they're also able to slide around, and that's what allows our fingers to not break all the time. And that compliance is very important. So you've seen a lot of recent research where they're looking at how to improve this and give that compliance in a joint, but also make it very strong at the same time. So the next, category we've seen a lot recently is rolling joints. So the rolling joints, it basically allows for that joint, when it gets hit hard or when it's in contact with objects, to move around and conform around the object itself. And so, like you're looking at the fave hand on the top right, what they do is these joints are basically, rolling contact, which means that these little pieces will move across each other and they're connected by rope. And that means, when they smash against the table, there's not actually one revolute joint, but there's many degrees of freedom that there's some compliance in. And the fave hand does this. If you see in a flex hand in the bottom right, see how they're moving it around, and those joints are still compliant and they're moving around and not breaking. And these sliding contact surfaces, they're very hard to design and they often have a lot of friction. But the good news is that they're very compliant for a lot of contact, which hands often experience. We've also been looking at this idea of a compliance in our lab. And one of the things that, we've seen a lot of is the idea of a living hinge or flexure joint. So if you think about your shampoo bottle, you think about the lid, that little piece of plastic in the middle is acting as a joint. So when you open and close it, even if the lid is all one material, you're still able to move, open and close your lid of the shampoo. And we're thinking about doing that in hands as well. You can design hands with flexure joints where it's rubber that, moves around when you actuate it with motors. And this allows for some translation and, non-actuated axis motion. And the soft material can be casted or 3D printed and can be very flexible. And tendons have become very, very popular, even with the rolling contact joints or through, flexure joints. There are many, many hands that do this now. The shadow hand is famous from OpenAI result from many years ago. And we've also been doing some work in the tendons area. We'll talk a little bit later about our own dash hand, the Loop Hand V2. Because tendons are, easy way to get the motors away from the hand, make the hand nice and small, and yet still pretty strong. And there's one last category of hands that we've seen recently is hydraulic robot hands. In this case, you have like a hydraulic fluid. It's pumped into a reservoir at very high pressure. And then the idea is that fluid can be pushed through the hand itself and actuate different joints within it. So as you can see on the right, this is the clone hand. Now, unfortunately, there's this pump and all these valves that maintain it, and it's very hard to maintain. But this is very cool work in the sense that you can make something very strong, and the hand can be very compact and human-like, and it looks very, very cool. Though it is very hard to control this and maintain it and create this system, but it's something that people have been working on in future research. So now I'll pass over to Nanya to talk a little bit about some of our work, looking at different types of joints in robot hands.
So this work we did like 2 years ago. This is an open source hand, which has the motors directly on the joints. It's completely rigid, but it's still useful for many machine learning applications, which we'll talk about. So as I talked about in the beginning, MCP joint design can have a big impact on how dexterous the hand is. Humans have like a ball joint on the MCP location, but ball joints are really hard to make. So typically what's done is you add 2 motors, one after the other at the MCP location. And the axes and order of these motors are typically very important. So let's take a look at 2 hands. So here we have the Allegro hand. And what happens is, because of the design of the MCP joint, in the extended position, the joint loses a degree of freedom. So when the finger spins around, the fingertip position doesn't actually change. So that degree of freedom is completely useless. So in the power grasp position, you lose a degree of freedom. There's another hand called the C hand. which has a different axis at the MCP joint. And this has a different problem. So while it doesn't lose a degree of freedom in the extended position, it loses that degree of freedom in the curled position. And what this leads to is bad dexterity in precision grasp positions. So in leap hand, what we did is we changed the order of motors at the MCP joint. And what this leads to is this universal joint mechanism where we never lose a degree of freedom. So if you look at these two other hands, what these hands have is the motor that controls the rotation around the finger axis comes before the motor that controls the flexing. Can you press next? Yeah. So what that means is that there will be some pose for the finger in which the rotation axis gets aligned with the finger axis. And in that particular pose, you hit a singularity and the finger loses a degree of freedom. But what we did in the leap hand is we switched the orders of these motors so that the motor which controls the left to right movement of the finger occurs after the motor that controls the flexing. And what this leads to is that the axis of the rotation never aligns with the finger. And so we never lose a degree of freedom. So we actually see that this leads to benefits on the metrics I outlined above. So we get higher opposability, thumb opposability volumes, higher manipulability volumes. And practically speaking, we are able to do tasks which require in-hand rotation at the fingertips, as well as in-hand rotation in this power grasp position. Both of the tasks work really well with the leap hand. And because the hand is completely rigid, you can actually easily model it in simulation. So there's this open source specification of the hand, which you can put inside a simulator and train with large scale RL. So as an illustration, we train this in-hand cube rotation policy. And the interesting thing is because it's trained with learning and it gets a history of joint angles, it can implicitly estimate the state of the cube. So there is no perception. It just uses a history of joint angles to estimate the state of the cube.
Cool. Thanks, Ananya. Part of the thing about putting motors as a joint, it's very important what motor you choose. So for us, we found, the most strongest and the lowest cost, motor that we could find. It also had the servo and all the angle sensors in it. And we made leap hand very, very easy to design and very, very strong. So it's been one of the, easiest to use robot hands in the category of motors in the joints. And we show a bunch of different results here. This is me doing teleop from one webcam, and we're able to do teleop on a bunch of different tasks just by using one webcam. And we beat, the Allegro hand baseline pretty easily on these tasks. And we also show autonomous results as well. So here we use some internet videos. We pre-train it to get the robot, give the robot an idea of what the human hand motions are in the videos. And then we use that as pre-training and then fine-tune on a few teleop demonstrations. And we can see that leap hand can perform a variety of different tasks. Leap hand has been the leading open source robot hand right now. It's really the best first intro into robot hands, and there's a really big leap hand community around it. There's many works. DexCap is one of my favorites, Stanford, and there's over 100 available. And I know at Berkeley there's one also in Jitendra's group, and also in a couple others at Berkeley as well. However, as you can see, there's still a gap between robot hands and human hands. You look at your human hand on the left and the leap hand all the way over on the right. The leap hand is still a little bit bigger. And we're not really emulating the skeleton and the skin of a human hand. And we really want, still that dexterous kinematic structure we got from leap hand, but also improve on the different grasp types we can make. So one of our first attempts at this was looking at the tendon-driven design. There's many robot hands out there, and we tried to make our own. So you can see on the bottom left, there's 3 different tendons pulling on different parts of the finger, and these fingers are 3D printed really easily. And there's a bunch of control that I won't go into, but how you tension these tendons and how you control them to know where the fingertip is actually quite difficult. And you can see on the top right, the nice thing about hands like this, when they're soft, is that you can bounce them on the table and they don't break. This is a real concern with robot hands with all these different little joints that can be often fragile. But we found there's some drawbacks with this naive design. When you use all these tendons and you have this flat palm, you lead to pretty poor grasping. Like you see this hammer in the palm, and with this flat palm, the hammer is just sort of sitting in the fingers. It's not all the way curled. And also the softness is maybe too soft. You see the finger can twist in all these undesirable orientations, and that's good, but maybe you don't want too much. So this leads us into our newest work, Leap Hand V2. And sort of the idea is, how can we think about how the human has all this bones and skin. How do we combine also soft and hard material? Like if you think about the human hand, the bones are giving you a lot of rigidity, and the fingernail actually helps you with grasping. That fingernail being stiff on the back helps a lot with your grasping. And in the robot, you see in the cross section of our finger in the bottom right, we also try to imitate that. So the white parts of that finger are the bone structure, and then the flexure joint is the soft material in between. And the nice thing about this, it still twists and bends without breaking, and it's really strong. And we can 3D print this all as one piece on multi-material 3D printers. And we came up with this idea to do this, and I think it's been a very strong robot hand that's also very durable. And another thing we introduced to make the palm better is we add 2 motors into the palm. So if you look on in the middle on the bottom there, there's this M1 and M2 motors that actually actuate the hand to really make it close really tight. And as Ananya talked earlier, the thumb to finger opposability is very important. And by making the palm actuating, it increases the amount of pinch grasp that you can do by a lot. And that allows you to do a lot more tighter grasping and better grasp in a variety of different tasks. And of course, we're in academia. We really want to target this hand towards ML research. So it's still pretty low cost and easy to assemble. And we'll provide a URDF and teleop code for it. So I want to talk a little bit about some of the results on some of our recent paper we've been working on. There's been a lot of work in the humanoid space in terms of how do you control robot hands. We've also been using, a motion capture glove. You can see Yuong here, one of our master student collaborators. He's controlling our robot hands and the robot arms using a Jello plus glove setup. And our sleep hand is nice and soft, and it's able to grasp things like grapes fairly easily. We also saw some autonomous results doing behavior cloning. So these are our 2 leap hands on our arms. And we train this, this is diffusion policy. And the nice thing about this is that because the fingers are soft, we see the plate and the 2 arms sort of interacting with the object. But we see that even with them twisting at slightly different rates or something, the soft hand and the fingers are able to comply around the object around it. And this is why a lot of people in the robot hand community have been very interested in compliant fingers in general. And because, we have a human-like size, we can also use things like drills, which is very hard for robot hands to do, is because the drill is very heavy and it's hard to press the button. And you can see even autonomously, eventually the policy learns how to press the button. And we show some more results here. You can see even as the finger hits the table there, it's not breaking, and it's able to be compliant towards that those forces. We also saw some mobile results here. This is our LeapHand V1. A lot of people have been using LeapHand V1, and we can also use our motion capture gloves on that system as well. And this is a mobile base that we built just to test out robot hands more than to actually do a full-on humanoid. It's easier for us in this setting. So I think we've talked a lot about the different actuation designs, and there's always this battle between if you want motor-driven design or tendon-driven design. And LeapHand, very strong, and it's very easy because of the motor-driven. But it's a little bit on the big side. And as Nanya showed, we can do really good simulation of it and do sim to real. Sometimes the soft hands with the compliant fingers can be better for different stuff, especially teleoperation. But sim to real can be harder. But the good news is these hands can be smaller and more human-like size. And also I have links to some of our stuff if you're interested in looking more in detail on leaphand.com, as well as our recent work. Yeah, and that's it. That's all I have. Thanks. Do you have any questions, I guess? I guess we can't hear you guys.
Okay, now can you hear us?
Yeah.
Yes.
Excellent. So yeah, so this is the time for questions. So I think people in the class, why don't you just come up to the laptop and ask your question? Somebody must have questions. Just introduce us.
Hey, my name is Justin.
Hey.
Thanks for talking to us. I think the new LeapHand is super cool. I was gonna probe your, and the kind of measurement of dexterity of the hand by using the manipulability. I was just playing with my own hand during the talk, and I realized that I can't actually move this finger in some of the ways that your hand can actuate the last 2 joints. And so do you think that measure of manipulability is the correct one to use, or do you think it seems like there's kind of a gap between the conventional sense of manipulability and how human hands are actually able to manipulate objects? So can you comment on that a little bit?
Yeah, so I agree with you that like human hands would not be able to move your finger in this position. So I would say that's a limitation of a human hand, and it's still desirable to have robot hands which can do that. So the reason we actually built this in the first place, the first iteration of the hand that we had did not have this capability. And then we tried training this policy to rotate like very small objects or like a ball here. And it turns out that's really hard if the object is like sort of oblong, because you need the hand to be able to move the finger around the object. So this particular movement at this precision position is very useful if you want to do like fingertip manipulation.
I think the other thing to think about is when you're actually grasping, when you close your hand, your fingers are actually getting closer and closer together as you're grasping. So in some sense, you are implicitly having some of that degree of freedom as you close your fingers. And by adding that, when we do the teleop, we're able to, spread or put your fingers together as you grasp. And I think it does help. There's always a battle between how human-like you want it, or do you want it to be superhuman? And I think part of it for us is we're giving you superhuman joints in some sense, like more than what a human would have, to try to compensate for the fact that the hand is obviously bigger, and it's going to suffer in other ways. So it's almost like, I guess, a compromise in some sense, if that makes sense.
Yeah, that's interesting.
Yeah.
I have another question if no one else has. Thank you.
Yeah, thanks.
Hello. Thank you for the presentation. My name is Ethan, and hi. Can you hear me?
Yeah.
Yeah.
Hi. My name is Ethan, and I really like the demo about the grape manipulation. And what was like the policy that you guys use for it? And also, is it just grasping the grape, or is it also like pulling it off from the stem?
Yeah, so I think that exact task we're doing teleop, one of the problems with that exact task is the robot hand cannot touch, so it cannot feel what the grape in it. And also the human teleoperator actually cannot feel what the robot hand is feeling. There's no haptic feedback to the teleoperator itself, which actually makes that task quite tricky. So really the only way we're able to do that is because the robot hand is fairly soft and the compliance of the finger itself is not actually crushing the grape. So, if we were to look at touch sensors, which we are looking at actually now, the tactile feedback would allow a policy, like action chunking transformer, diffusion policies, what we've been using, either of those, to actually feel the grape inside and maybe pull in the right way. Right now, we can only do that task teleop, but it's something we'll probably look at soon. Yeah, it's a good question though.
Thank you.
Hi, it's me again.
Hey.
I wanted to push more on this. You mentioned tactile sensing and haptics. I wanted to get your thoughts on kind of the state of tactile sensing for hands and robotics, and then also haptic teleop interfaces.
Yeah, I think for tactile itself, this gel sight's been very common on grippers or for like Allegro hand or Leap Hand V1. But the problem is it's too big and too thick, and a lot of these sensors are still really too big. So I think a lot of these film-based sensors, I'm actually looking, in sort of the reskin style, very thin magnetic sensors, or like the resistive sensors. I don't know if you've heard of Stag or some of these other ones that are just like a resistor basically in a network, and then you can use that. There's very little work in this area because I think you have to kind of solve the robot hand hardware before you look at the tactile, and tactiles have, the sensors have to be very thin and very small, which makes it very hard. And I think also like it's a whole nother thing, of course, to train a policy to use that data properly, which is also quite difficult, I think, right now, and to collect enough data or to teleop. Like you mentioned haptics. To me, like haptics is very, very far away. There's some very early stage work in this, and there's very impressive work, but it's very, very hard to do. And I wonder if using haptics is sort of the right way to approach the problem, in the sense that if you just use your human hand and like grasp an object, you can feel it. And maybe if you just wear a human touch sensor glove, that's the way you should be collecting data and doing it. Or if you should really be teleoping, feeling the haptic feedback through and using touch sensors on the hand itself. I think haptics is very hard to set up and very, very expensive right now. Mostly it's like air-based or fluid-based. And it might take quite a while for us to look at something like that. But I think tactile sensors is more something that we're looking at pretty closely. Yeah.
What are your thoughts on force sensing, like proprioception within the joint itself?
Yeah, so Ananya obviously showed with Cinta Real that the proprioception is definitely very useful. And of course, this is one of the issue with tendon-driven designs is you lose some of that sensing. And I think proprioception will be useful for a while. Honestly, if you have it, you should use it. Yeah. Is there other people?
Hello, my name is Amish. I had a question about the sort of like fault tolerance that you kind of foresee being useful in terms of constructing these hands in the future. So like if you have like a fully activated hand, and then if one of the motors on this dies, like I think one of the benefits of having tendons is that you might capture some of like the interdependence between the different degrees of freedom in the hand. Is that something that's like an active kind of ongoing area of research of how to build in fault tolerance in case like one of the motors dies or something like that, that still allows you to get as much functionality out of the hand as possible?
And then, do you want to talk about that Centurial paper? There's some work in this, I think.
I'm not aware of any work which tries to like build in redundancy into the joints, but what you can do is, so if you can be robust to changing motor parameters. So that is something that is very common, and we do this in locomotion and so on. So what you do is when you're training, like let's say you keep running the hand for several hours, what happens is the motors heat up and then their properties will change. So they won't respond to PID, like the gains might change internally, PID gains. So typically what we do is when we train robot policies, at least in simulation, we domain randomize over these parameters. So we randomize the gains, randomize the motor strengths. And what happens is if you train an adaptive policy, then like maybe something like using like RMA or a recurrent network, then what happens is that this policy can learn to use a short history of joint angles to infer how the properties have changed. And this makes it robust to changing parameters. So that is, I feel like, the dominant approach. I don't know if complete failure occurs, then these things would probably not work. And so maybe it's useful to build redundancy over there.
Yeah, on the mechanical side, also, like you're right, the tendons allow like your last two joints. Usually, a lot of times they're often actuated together. So in shadow hand and in our leap hand, G2, they're actuated as one motor. And sometimes this compliance can help you with grasping. But yeah, if that motor goes bad, then of course you're going to lose those 2 degrees of freedom. I guess one of the things for us at least has been we make these hands open source and they're assemble them yourselves. They're very easy to repair and you can just recalibrate them, and it's very quick to get back up and running. And I know actually many humanoid companies are taking the same approach to fault tolerance, which is if it is really messing up, you just really quickly try to replace the finger, replace the hand, and keep moving. I think that's one way to get around it.
Thanks.
Okay, thanks a lot, Ananya and Kenny. So this was great. I was going to ask a question on tactile sensing, but I think you sort of already pre-answered it, so I won't ask it again. But really appreciate your time. What we're going to do now is my next lecture is actually on touch and proprioception. So in case you're curious to hear that, you can stick around.
Sure.
It's going to be about human touch and human proprioception. So it's all about sort of the neuroscience and psychology of that, which you may or may not care about. But our practice is that we take a break in the middle of there's a 2-hour class, so we take a break in the middle. So it's now 3:44 my time. So we're going to resume at 3:54. Okay. So there's a 10-minute break and it's at 3:54, and you guys should not feel pressured to stay. You can take off. It's up to you. Okay. So thanks. Let's thank the speakers.
Thank you.
Yeah, thank you so much.
Okay. Yeah. Can you send the slides to Toru so she can put it up on our website?
Yeah, I'll send it to her right now.
Okay. Okay, and recording has started. Okay, so in this lecture, I'm going to talk about touch and proprioception and the hand, but the hand more broadly construed. And here is what I want to convey in this in the rest of this lecture, which is that the hand is an amazing instrument. It is simultaneously a perception device, so kind of like a camera, and an actuation device, one which can change the world. So there is a sensory motor continuum of the human hand function. And that's what is shown in that top diagram. So at the one end, you can think of it as a measurement device. It's tactile sensing. So if you think of the fingers, they're a bit like cameras, right? They're measuring the world. Any object which comes in contact with the skin, we can measure some stuff from that. There is active haptic sensing. By that, I mean, you can move the fingers and the hand over in various ways. So there is a very simple experiment here that I want to tell you about, which is, suppose you want to know the weight of an object. Okay, how do you know the weight of an object? So one thing you can do is you can put your hand on the table, okay? And I don't know, I'm not seeing the feedback of what people in Zoom line can see. You can put your hand on a table, and then you put the object on it, and you can guess the weight of it, right? Okay, so the way the experiments are done by psychologists is that you try to distinguish between two weights. So you have a weight W1 and a weight W2, which are slightly different, and you're supposed to say which one is heavier, okay? And for some differences between W1 and W2, you can make that judgment reliably. Okay, and for some, when the difference is very small, you can't make it reliably, you make it a chance. And it turns out that that error, W1 minus W2, the norm of that error is typically proportional to the weight. So this is called a Weber fraction. So if the weight is 100 grams, then you can distinguish it from 106 grams. If the weight is 10 grams, you can distinguish it from a weight of 10.6 grams, something like that, right? Okay. It turns out that, so now you have a way to judge the utility of a hand as a weighing device. It turns out that if you just put your hand flat on a table where the hand is stationary and you try to judge weight, you can get a certain accuracy. Or you can hold the object in the hand and move it about, okay? And you are more accurate, much more accurate that way. And the accuracy is about 6%. The Weber fraction is about 6%. So this is active haptic sensing. And then we can talk about the hand as an actor, the hand as changing the world in some way. And that's we distinguish between what are called prehensile movements, which involve grasping, and non-prehensile movements, which include everything from gesture, typing, piano playing, etc. So this is the continuum, if you will. At the one end, it's a pure sensor measurement device, which does not change the world. It just tries to learn what the world is about. And then there is the other extreme, which is the hand as an action device, where you apply forces and change the world. Okay, so I'm going to start on the sensory side of this. And I'm going to start with talking about proprioception. So proprioception is a genuine discovery of modern science, because at least in the Western tradition, Aristotle said some things, and then people said, okay, since Aristotle said them, they must be true. And Aristotle listed 5 senses: vision, audition, touch, taste, and smell. And this is what kids learn in school. So in school, they're taught about the 5 senses, and it really goes back to Aristotle. Okay. And we should actually do some research on this across different cultures, in Chinese culture or Indian culture or various other civilizations. Do they have the same 5 senses? I'm not sure. I think we are just being very ethnocentric here and regarding Aristotle's word as final. Okay, be as it may. There's this guy called Charles Bell in 1826. He was a Scottish scientist and surgeon, and who really studied the hand and so forth. And he proposed a 6th sense, which he called the muscular sense. And this was subsequently renamed by Sherrington as proprioception. So what does that term mean? Receptor is just some measurement device. Proprio means about yourself. Proprio, it's the same root as proprietary, property. It's like your personal property. It's about you. So proprioception is to be contrasted with exteroception. Exteroception is about the external world. Proprioception is about your internal world. And the idea of Bell and Sherrington was that even when even when it's dark, so at night you wake up from the bed and you don't have the lights on, you know various aspects of your body. When my eyes are closed, I can reach and touch my nose. Okay, I know about the rough positions of my joints in some ways, and so I know where my body is and where the parts of my body are relative to each other. Now, the question then is, how is this implemented? How does the body implement it? What's the neuroscience of it? And that leads us down two paths. One is the musculoskeletal system. In the musculoskeletal system, how do we know about your joint positions, velocities, etc.? And the answer is that it's because there are sensors in the muscles and tendons and joints. In my next slide, I'm going to give you a figure. And then there is the vestibular system. So the vestibular system is in the inner ear, and this is what accounts for your so-called sense of balance. And it has two components. They are the semicircular canals, which essentially measure your rotation, and then otoliths, which measure translation. So think of in your cell phone, your iPhone, you have an IMU, which actually does these. That said, I'm not going to talk much about the vestibular system in the rest of this lecture. Sometimes people use the term kinesthesia, and kinesthesia refers to the first of these components, the musculoskeletal system. Now, let me get more specific. So here's a figure which tells you about kinesthesia or the proprioception based on the musculoskeletal system. So it's pretty simple. How do we move? We have muscles which are connected by tendons to bones. And then there are sensors inside the muscle spindle. Okay. And there are a number of these, and they vary according to the muscle, big muscle, small muscle. So I actually looked this up. So the muscle which enables you to move your index finger side to side, this one has 34 of these. Okay, and your biceps have 320 of these. So there are a precise number that I can give you of these sensors. There are also sensors in the tendon. These are the so-called Golgi tendon organ. So these are sensors in the tendon which connects the muscle to the bone. And then there are joint receptors. So joint receptors are like basically in the skin at the joint, and they are kind of weak. They're not very accurate. When you flex or extend a joint, then what happens is that the skin at the joint stretches, and then these sensors detect that. So there is a belief that these are mainly used for you not going out of joint limits or not breaking your joint by trying to go too far. Okay, so these are it's pretty straightforward that the stretching of the muscle is going to be related to the joint angle, and if you can measure that signal in the nerve, that's going to be useful to the brain for figuring out joint angles. Okay, so I think I dealt with the musculoskeletal system. Sensors in the muscles, tendons, and the joints. Okay. Now, what about robots? Okay, I think you got a bit of the sense of this in the previous lecture, and in the even more previous lecture where we talked about robot kinematics and dynamics. So I will just do the simple-minded story here. So the simple-minded story is that suppose we are using motors. Well, then what is a motor? We are using these electric motors. So electric motors have shafts which rotate. So therefore, you want to know the angular position. And those are, there's a rotary encoder will sense that angle. Okay, so that gives you a measurement of the equivalent thing in the human body. It's achieved by these sensors in the muscles and the tendons and so forth. Okay, now what's the sense of touch? So that Aristotle did know about the sense of touch. So that was in his list of 5. So how do we define this? It's an amazing system. I mean, I knew a little bit about it, but then I took the trouble to study it more extensively in the last couple of months, and it's super impressive. I was a vision chauvinist. I always believed that vision is the most remarkable of senses because it is very, very sensitive, and yet it operates over a dynamic range. So in the case of vision, you have like 100 million receptors. A single receptor can detect a single photon. That's like the smallest you can get. And then it can operate in bright sunlight. So that's like a dynamic range of 11 orders of magnitude. It has very good spatial precision, temporal precision, etc. But I've been impressed by the sense of touch. It's actually, in some ways, it's even more remarkable than vision. Okay, how does it work though? Very important point here is that the skin is flexible. So when you press on any surface, when an object presses against your finger, for example, what's happening is that the skin is stretched, and the area in contact increases. It increases can be as much as like 70%. So it's a significant increase. Other features on the finger which are useful, there are fingerprints. So these fingerprints help provide friction. So when you are holding some surface which is like wet or slippery, then actually they come in handy. So, okay, so really it starts from the skin itself. And then there will be some mechanical deformation of the skin because you have applied some pressure on the skin, maybe in a localized way. And this is detected by so-called mechanoreceptors. What does that term mean? Mechano means mechanics, mechanical. That's a word, right? Receptor is just like we already saw in the context of photoreceptors. Photoreceptors measure light. Mechanoreceptors measure some mechanical change. Okay, here is a slide which shows what they are and where they are located. So there is the skin that we have. It's of 2 types. It's the so-called hairy skin, and well, I would have called it non-hairy skin, but the biologists use the term glabrous skin. So the canonical example of that is the skin on your palm. The skin on the palmar side is which of these? Glabrous. The skin on the other side, the dorsal side, is hairy skin. Okay. Okay, so the most sensitive areas are typically glabrous skin. Okay, the fingertip is a very sensitive area. The lips are a very sensitive area. Okay, and underneath what you have are these various types here. There's the so-called, let me see if my mouse works. Yeah. Okay, so let's go through the names. There are 4 names to know here. The Merkel disc receptor, the Meissner corpuscle. So most of these are named after Germans or Italians from the 19th century. These 2 are Germans, and then there is Ruffini, and then there is Pessini. Okay, so there are 4 types of. So these folks got their names because they discovered them sometime in the late 19th century. So okay, so let's try to remember the names: Meissner corpuscle, Merkel disc receptor. Okay. Eventually, the names are not important, but what question?
So you mentioned before vision sense, and I feel like for vision, like most of the heavy lifting is not by the eye, but actually by the brain.
So the same is true here. It will always be the case. We do not see just with our eyes, we see with our brain. The same, we do not touch just with our touch, but with our brain. Yeah, that's always the case. Yeah. Okay, so let's see. Okay, so the Meissner corpuscle and the Merkel disc receptor, the thing you should note is that they are high up. They are pretty close to the skin surface. Then deep down is where you have this Pacinian corpuscle and the Ruffini endings. So these are slightly lower. And this, you can immediately guess what that implies, right? So there'll be a more close, more delicate spatial sensitivity and resolution in the sensors which are closer to the epidermis, right? So the Merkel and the Meissner will have more fine-grained spatial resolution, whereas the Pacinian corpuscle and the Ruffini ending, since they are lower down, they're going to be kind of integrating over a larger area of the skin. So that you can intuitively guess just from the anatomy. Okay. Now, so when the skin is pressed, there is some activation, right, of these various sensors. Just like when light hits your eye, there is an activation of these photoreceptors. And then the photoreceptor, so the photoreceptor, there's a photon that is received, and then some electrical signal is produced, and then it is shipped through the optic nerve to the brain. So the same kind of thing is going to happen in the context of touch. Okay. And then our brain is where the perception occurs, right? So in the case of light, that single photon leads to the subjective perception of something twinkling in your visual field. Well, here it's going to be perceived as some kind of touch or pressure or whatever. Okay. There are other receptors underneath the skin which sense warmth, cold, pain, itching. And these are important for human survival, but I won't say more about them. Okay, I'm focusing on the ones which are going to be more useful from a robotics point of view. Okay, so now we had these 4 sensors. So there are Merkel, Meissner, right? Ruffini endings and Pacinian corpuscles. And the first, question.
Things we can sense like heat, cold, pressure, etc., that they go through the same nerves close to the skin, or the same sensory structures will sense multiple things, or are they all distinct?
No, they're never. See, what happens with sensors is that they get activated by certain stimuli, and then there is a nerve impulse which goes from that nerve, and then it is bundled up and it's received ultimately by the somatosensory cortex. And it's the job of the somatosensory cortex to interpret what has happened. And let me make an analogy with color vision. So in the case of color vision, what's happening is that there are 3 different receptor types, but all 3 receptors are activated whenever you see some scene. But they are differentially activated, and it's a job of the brain to interpret the differential outputs of the different receptors to perceive the scene. Okay.
Do you ever have like one nerve that's receiving information from multiple sensors?
That can happen, yeah. You can obviously merge. I mean, in the visual system, whenever I don't know details about the touch system, I'm going to use vision as an example because I know that well. Okay, so in the case of vision, we start with 120 million receptors, and the optic nerve has just 1 million fibers.
But you never have like a nerve in the retina or something that's connecting to 2 sensors in different types.
You have various stages of processing. Yeah. Okay. So back to this picture. So there is a concept of receptive field in neuroscience and receptive field in neural networks. So receptive field for a neuron refers to what are the, so in the case of say a neural network which is processing visual information, the receptive field of a neuron refers to which are the pixels in the input, which if you change, you can change the output of that neuron. So we can talk about the receptive fields at every stage of a neural network. And at the early stages, the receptive fields are small. And at the higher stages, the receptive fields are large, right? So initially, they might just respond to a vertical line in a few pixels. At the late stages, they might respond to a face anywhere. Okay. So the receptive fields of these Merkel discs and Meissner's corpuscles are small. You can see that in the diagram here, right? They're all small. So they're quite acutely sensitive to something like the density of these, I think these Merkel receptors might be like every 1 millimeter or so. Okay. Then these, on the other hand, these Ruffini endings and Pacinian corpuscles, they are deeper in the sense of underneath, lower down the skin, and then they have big receptive fields, as is shown in this figure. Okay, so that's one. So spatial resolution, these top two have low spatial resolution, which means that they'll be useful for fine spatial discrimination. The bottom two will be less useful for fine spatial discrimination. The other dimension is temporal frequency. So do the responses change when the input changes? Because you can have, because if you go back to your your first signals class on Fourier transforms, low spatial frequencies, high spatial frequencies. Similarly, you can talk about low temporal frequencies and high temporal frequencies. So between these, there's this term SA and RA. So what do you guess SA stands for? Slowly adapting, and RA is rapidly adapting. So which one should deal with fast changes? Rapidly adapting. Good. So our colleagues know how to name their systems well. Okay. So when you have, for example, a steady, so in the case of, let's look at Meissner's corpuscles. So they are rapidly adapting. What that means is that when I press something on the skin, as soon as that event happens, there is a sharp change. And so it's going to respond it very fast. Okay. So now if you look at the bottom, this is the spike train. So the spike train of this RA1 here is Meissner's corpuscles. So RA1, as soon as there is a stimulus, which is shown here. So the stimulus was 0, and then it jumped up. So there's like a step change. As soon as that change occurs, you got lots of spikes, right? And then once it became steady, then it stops. So it doesn't respond to steady change. So it's like you need high frequencies in the temporal dimension to keep this neuron firing. When it becomes constant, it doesn't care. So constant steady pressure, it doesn't care. Now this is not true, for example, for the Merkel discs, where a steady pressure it's still responding to that. So this combo of these 4 types, low spatial frequencies, small receptive fields versus large receptive fields, rapidly acting versus slow acting, that combination gives you that kind of diversity of responses, such that after that, the brain can do whatever interpretation it does. So again, my analogy is that to color. You have 3 different photoreceptor types, which are sensitive to light, different spectral distributions of light, and the combination of the 3 responses gives us a very good signal. Yeah, now there were some questions which I can answer now. Yeah. Yeah, correct. Yeah, exactly. Event camera is a good analogy. Oh, that I want to get into, but look it up. Okay, yeah. Question. Correct. Yeah, multiple small ones. Yeah. Okay. So now I have an example here from this book, Touch, the Science of Hand, Heart, and Mind. So this guy comes up with some good, cool examples of which sensors are being activated. Actually, everyone is being activated, but which is more important? So the task is the following. So I park my car. I need to fish a quarter out of my pocket. Well, now you might use your cell phone, but in the era when you had to put coins into parking meters. So first you reach into your pocket. In your pocket, there's some coins, there are your keys, there's your wallet, there's your cell phone, and you have to fish something out. What are you going to do? You're essentially solving an object recognition problem with your fingers. But what's likely to be the most useful signal to distinguish, for example, a quarter from the dime? So if you think about it, the most useful is clearly the Merkel disk, because sharp edges are going to be detected very nicely by the Merkle disk. They're going to respond, and by feeling the boundaries of objects, you will find that round kind of thing, which is the quarter. Okay. The second task is, now you found that coin, you fish it out of your pocket. Oh, I should have had a coin in my pocket. Okay, I'll fake it with a pencil. Imagine that this is a quarter. Now what's happening there? So now it's steady, right? So I'm the Merkle disk is giving me a steady signal. But the Meissner is actually quite useful, because if I don't apply the right amount of force, I apply too little force, what's going to happen? It's going to start to slip. If it's going to start to slip, that's going to activate the rapidly adapting receptors, the Meissners. They are going to fire, right? Because they fire whenever you have sharp changes. And then in a very quick loop, the brain gets the signal and responds to it. And what you do is, when it starts to slip, you just apply more force. And when you apply more normal force, there's going to be a greater frictional resistance, and then the object will no longer slip. And this is happening sort of subconsciously. So when we hold objects, we don't apply huge amounts of force. We apply just the right amount of force. So the force, when you hold up an egg, right, you don't want to be applying huge amounts of force. When you are doing rock climbing and you are hanging by your fingers, you better apply enough force, otherwise you're going to fall off and die, right? So that kind of adaptation is based on sensory feedback. And this is something we would love to give our robots. Okay. And then you insert the coin, and then now what's happening is that now the response is essentially directed towards your full finger or hand, and it's now more distributed. And at this point, these Pacinian corpuscles are going to be useful for you. Okay. Yeah.
When it comes to localizing something with a small and large receptive field type of neuron,
yeah,
does the brain index a small area directly, or does it have to get there sort of through a hierarchy of?
I mean, we don't know the full details, but there is we can do psychophysics to judge how good humans are at discriminating, and they can discriminate two stimuli which are about 1 millimeter apart on the finger, and that is roughly the same as the spacing of these sensors in the fingers. So it's like in your eye, you can distinguish stimuli which fall on one cone versus the next cone over, and something similar. So we are not, so where we care about exquisite spatial sensitivity, such as on the tips of our fingers, the system doesn't build something fancy and after that lose it by averaging it away. It makes full use of it. Okay. Okay, so I think this example is now done. Now what happens is that, now somebody asked me, do we see with when we see, do we see with our eyes or do we see with our brains? And the answer is, you obviously see with both. I mean, if you didn't have the photons falling on your eyes, you wouldn't have anything to start with, but the process is all the stages matter. So the stages so this is a slide which shows what's happening in the brain. So in the brain, there is so the term used is somatosensory cortex. So the somatosensory cortex is getting the signal from these nerves which are going from the hand, then they go through the spinal cord, they go up to the brain, and the somatosensory cortex is kind of in this area of the brain. It's near the so-called central sulcus, okay, of the cerebral cortex, and this is next to the somatosensory area. How do we know that there's a somatosensory area? So the neurons there are activated when you activate various parts of your skin. Maybe your fingers, maybe your tongue, maybe your lips, maybe you push a pin on your back, etc., right? So that's how you can map out the somatosensory cortex. And the somatosensory cortex, very conveniently, is right next to the motor cortex. So let me show this figure. So in this figure, if you look, there is the somatosensory cortex, and it's right next to this other strip, which is the motor cortex. So the motor cortex is the one where there are neurons which fire when you decide to move your hand and pick up an object and so on. So it looks like the brain is doing the sensible thing in terms of the wiring. So you're getting this input from the sensors on your fingers and so forth, as well as proprioceptive input from your muscles and so forth. It's all used together. And then it is triggering action in the motor cortex where you're causing activations of the muscles which move your arms and thumbs and fingers and so forth. Yeah.
Is this mapping learned from interaction, or is it like a static architecture?
It is not fully static, but it is somewhat it's somewhat repeated from person to person. But there are these classic experiments which show that when you on both the motor side and the sensory side, if you use something more, so like pianists, so their representation of the fingers is going to take up more area. Okay, you can do things like, of course, you can do cruel things like chop off a finger, and the representation of that finger will shrivel, and other areas will sort of take up those neurons. So there is plasticity in the cortex, and it was first established in this setting. Okay, what I show here is what is sometimes referred to as the sensory motor homunculus. And this is like from this guy Penfield, who was doing these experiments around 1950s. For people who had epileptic seizures, they would cut open their skull and they would have to do some stuff to reduce the risk of seizures. But when they were doing that, they would be able to do experiments on them. So it turns out that the entire body skin surface is represented on the somatosensory cortex, but not all parts have equal importance. So that the area, the real estate in the somatosensory cortex is partitioned out according to importance. So, so you see there's a lot here corresponding to, wait, let me see my, so like the hand, the fingers, the thumb, the forearm, elbow. Now you see there's like the legs, not so much is being used up there. Okay, there's a lot being used up for the face and so forth, right? So this is on the sensory side, and this is on the motor side. On the motor side, again, you have so this is like what neurons are activating when they are firing, then some finger moves or something like that, or your elbow joint changes from flexion to extension. So that, okay, so that's this. This is just roughly giving you a sense of the importance of the different areas, which is roughly related to the density of sensors. So if you think in vision we talk about the fovea. So in the fovea, you have a much greater density of photoreceptors corresponding to a certain visual angle. And then as you go into the periphery, you have a lower density of photoreceptors. What's the equivalent of the fovea for the skin tactile system? It's like the finger. The fingers have very high density, right? Whereas the back, the skin on your back has much lower density of these receptors. Okay. Okay. So that was one point. Next point is that all these areas on the cerebral cortex, they have names and numbers. I mean, so like the visual areas are called V1, V2, V3, V4. So here they have all these areas called M1, M2. So people are not super inspired, but that's good because it enables us to remember them. M1, M2 refers to like the motor cortex areas, 1, 2. What do you think this S suggests? Somatosensory, yeah. And then there are numbers. And then there are these kinds of wiring diagrams which tell you how the input comes in. So the input comes in from the skin through the thalamus. So the thalamus is like a way station before it gets to the cortex. Then you have this somatosensory cortex, and then after that there are these two streams, one called the ventral stream and one called the dorsal stream. And this is kind of interesting because, again, I will refer back to my vision experience. People have constructed diagrams like this for the visual system. Okay, so whenever I'm at a loss to understand the somatosensory system, I just refer back to the visual system. So in the case of a visual system, the visual system, people have made these diagrams up, which correspond to the different areas of the cortex, starting from kind of the retina, basically. The RGC is retinal ganglion cell. And then there are these various areas of the brain and what's connected to what. Okay, and but the next part is kind of interesting, which is that after the early generic visual processing areas, you get two streams. One which is called the dorsal stream and one which is called the ventral stream. Okay, the ventral stream is very easy to describe. So the ventral stream, so dorsal and ventral, dorsal means on the back, ventral means towards the front. So you can see the arrows. So this is supposed to be a view of the head, where the back is on the right hand side. Okay. So the ventral pathway leads to what's called inferior temporal cortex. This is where object recognition happens and face recognition happens and so on. Okay, and then there is this dorsal pathway, which you can see where it's going. It's going to the same area where you have somatosensory cortex and motor cortex. So that should give you a clue. It's like trying, okay. So this was sometimes described as a where pathway, but some people just use the term the how pathway, because it's really about vision for action. And when you want vision for action, what do you want to put together? You want to put together vision. You want to put together the mapping from proprioception, the mapping from touch, and then you want to have it next door to the motor cortex, which is where you activate the various muscles. So it's all makes sense. You want to be neighbors to the people whom you want to influence. Yeah, question.
Is the ventral pathway closer to language?
So yes, the ventral pathway you can think of as basically, to me, all these large language models or LVMs or what VLMs. So VLMs are ventral pathway. So the people who insist that all of intelligence is solved by VLMs, I completely disagree, of course. But they are basically focusing on just this part. So when you have GPT-4O or V or whatever, what it does is it takes an image, recognizes some objects, converts it to some tokens, and then the rest is all mushed together with language. Well, that is the ventral pathway. But that is missing out the dorsal pathway, which is very important. If you didn't have the dorsal pathway, you wouldn't have survived, because the value, I mean, vision guides action, and that's how you live. I mean, you have to find food and so on. Okay. So here's the cool part. You have these two streams also from the proprioceptive and tactile information. So there are two streams here. Notice that there is a ventral stream and there's a dorsal stream. So the ventral stream, what is that? That is the hand as a sensor. When I go to a store and I'm looking at some fabric and there's some silk and I'm running my fingers over it and I'm trying to judge, is it nice, smooth silk or not? That's a judgment of a material property, right? That's not immediately guiding action. It is guiding perception. It's like attributes of various objects. So our attributes or objects are judged visually, but also through your proprioceptive and somatosensory systems. Okay, and then there's this other pathway, the dorsal stream. And this is going to, for example, when this object starts to slip and you need to immediately act, well, that's clearly that other stream. So both streams are important. Both exist for vision. Both also exist in this setting of proprioceptive information and touch information. Okay, so this is this is a summary of what I said so far. So there's the what system, which is kind of recognizing objects and measuring their attributes. And then there is the where system, which you could think of as spatial location, but actually, more importantly, it's guiding action. It's the how system. So I think I somebody asked me a question, so I already said this. The ventral stream connects to multimodal conscious perception, object names, attributes, VLMs. So VLMs are the ventral stream. The dorsal stream connects to action, and this is in the spirit of perception guides action. So today's lecture is all about proprioception, but the next lecture is going to be about vision guides action. So basically, I'm going to be talking about the dorsal stream with respect to vision. That will be next week's first lecture. And I have the example of slip, but there are many others. There's just one example. So any question on this? Somebody in, if there's a question on chat, Toru, you should, no, nothing. Okay, yeah, question.
How far back?
No, I think this is they're in primates, yeah. But I don't know enough to tell you about what. There are different animals, among different mammals, the importance of different systems varies. So for example, rats pay much more attention to the somatosensory system, right? So they have these whiskers, and with this whisking movement, they are measuring properties of the world. So we are visual animals, but not all animals are visual. I mean, they all have these different capabilities, but bats are relying more on audition, we are relying on vision, rats are relying more on somatosensory, and so forth. Yeah. Question? Can you speak louder, please? Yeah, no, so I'm saying that, so that may come in through more higher level planning. Okay, so when we think of action, again, we don't know the details for sure, but my rough speculation would be something like this. So there is action is always hierarchical and at multiple time scales. So there needs to be some action that you're taking at 100 hertz, some at 10 hertz, some at 1 hertz. So the decision that I make, which is that I need to go get a cup of coffee, is operating on a slow time scale. And it may be that it got triggered because I saw some ad of somebody with a nice cup of coffee, right? Okay. As opposed to something which is happening at 10 hertz or 100 hertz, which is when I'm holding the coffee cup and I don't want it to slip. So conscious perception obviously plays a role in guiding actions at a more higher level. Just may not be doing so at the very fast control loop at 10 hertz or 100 hertz. Yeah. And we don't, lot of this is, particularly these higher kind of layers, of we just, not enough is known from the neuroscience. Yeah.
Is there enough sensors to build robots that can somehow experience what is doing, or do we need the material science to?
Yeah. Okay, so I'll repeat the question for people in Zoom land, which is that given the sophistication and complexity of the touch system in humans, where do we stand today in robotics? And the answer is we are very far back. So my way of saying this is that in vision, we are in robotic vision, in terms of the hardware, we are as good as humans or even better. But in robotic touch, no. So that means that over the next few years, there will be significant advances that need to occur, which will enable us to have better sensors. So it's right now, the situation seems to be that there are just not that many people working in this area. So in my view, the area of tactile sensing just needs lots more research. And one of the issues was that in the past, if people built these sensors, they didn't know how to use them well. I think that with the benefit of the deep learning techniques in robotics, we have much more advances in how to use these kinds of sensors. So I think that now when people build these sensors, we actually find good ways of using them. And what you need is this virtuous cycle where somebody builds good sensors, you use it in good policies, people are impressed by the results, then they feel motivated to put in more money in research on better sensing and so forth. And advances can come from anywhere: electrical engineering, material science, mechanical engineering, everywhere. But this is a good point. Okay, so let's go back to the sensory motor continuum of human hand function. And I spent, I gave you like the basic sensory hardware. So that was valid for passive tactile sensing. If I kept my hand stationary and I just put an object on it, or I move an object on it, this is passive tactile sensing. Now I want to refer to active haptic sensing, where you choose to move the sensors. So you choose to move the hand. So my example earlier was, I have an object, I want to know how much it weighs, or whether it weighs heavier or lighter than object A, between object A and object B. So I'm going to put it in my hand and I will move it up and down, and I can do a better job that way. So this is what we mean by active haptic sensing. So I do not wish to at all imply that vision is always passive. Vision is also active. And in the case of vision, it comes from the fact that we have a fovea. So when my attention can be attracted from anywhere in the room. If somebody asks me a question, I'm going to turn my head and my eyes to look at that person. So we foveate, and that is active sensing. Other examples are, I'm looking at some image and I'm doing visual search. I'm trying to find something. So active vision also is not just passive, it's also active. Okay. In the case of touch, the same thing. So the slogan here is that it's not the Merkel receptors which are your which is what achieve touch. It's the hand that achieves touch, and the hand that achieves touch through the combination of the active movement of the hand, okay, and then of course the measurements that you get from the sensors. Is that clear? So let's go into, okay, I've given you the basic examples, but now I want to play this for you.
One of my favorite books. The Lion, the Witch, and the Wardrobe. Once there were 4 children whose names were Peter, Susan, Edmund, and Lucy. Foxes, said Edmund. Rabbits, said Susan. But when next morning came, there was a steady rain falling. Of course it would be raining, said Edmund. My name is Mary Wagner, and I'm the Braille instructor here. I've been reading Braille since I was 3 years old. It is a major passion of mine, and I'm so excited that I get to teach it every single day. Reading is just essential anyway. Unfortunately, a lot of blind children fall through the cracks because they're not exposed to Braille at a young age. I was actually very, very blessed. My vision teacher sat down with me at 3 years old and began to teach me the Braille alphabet. If it weren't for Braille, I can't even imagine where I would be education-wise. It's just like the print on the page that sighted people can read. Braille is a way for you to get the same information, so that that story that child really wants to read, they can read that same story that their friends are reading. The only difference is they use it with their fingers instead of their eyes. If I were to explain it to an adult, I would say it's a series of dot combinations. So there's 6 dots, and each dot has its own number. A is dot 1, B is dot 1 and 2, C is 1, 4, D is 1, 4, 5. And as you progress in learning the letters, there's a slight pattern, and it kind of starts to make a little more sense. So I wouldn't say it's mathematical. It's just a matter of getting the shape in your mind and letting your fingers do the reading. This is the stylus. What this is doing is punching the holes in the paper. And this is the slate. Each one of these little squares, they have 6 little holes inside them that mimics the Braille cell. So the reason you're writing from right to left is because when you turn the paper over, you're going to read from left to right. If I'm writing a long document, it's just more conducive for me to use the Braille writer. This is dot 1, dot 2, dot 3, and this is dot 4, 5, 6. So you're only using these 3 fingers. You'll see why I like this better. I mean, it's a lot louder, but I can get a lot more accomplished with this. No parent of any sighted child would be content with their child just listening to an audible recording. They want their children to read. If your child is blind, they have the same right to learn how to read as a sighted child. And with technology being what it is, they have Braille displays so that any book can be in a digital format and translated into Braille by using the Braille displays. Braille could definitely be taught to someone who is not blind. Just like there are classes for communities, in sign language, there should definitely be something like that available for those who are interested in learning Braille. Because like you said, you never know if your vision is going to go. Reading is amazing. I have had a lot of experiences in my life where I've been able to just become a part of the story. I've always loved stories. So the fact that I can have the same access to information as any sighted person who loves to read, it's definitely a blessing. I'm thankful that it's available for the blind.
Okay.
My favorite books.
Okay, so of course there's an emotional aspect to seeing this, but now we can be all nerdy and engineering about it. But here are some numbers on how impressive this capability is. So first of all, you got that key technical point, right? 6 binary, so therefore 2 to the power 6. If you think of the alphabet, it is 26 letters. Probably there are all the digits, so you can see how it would work out. And so this fellow Braille was a French guy who worked it out about 1820s, 1830s, something like that. There used to be some other system, but he figured out essentially what's a good coding system. And then it took a while before it got accepted, but it has got accepted. But average Braille readers can read at 120 words per minute, and experts at 200 words per minute. Okay. And this corresponds to recognizing a character at 50 milliseconds. And to see how impressive this is, when you are sighted readers, like people like us, our reading speed is 240 words per minute. So it's like a factor of 2, only a loss of a factor of 2 compared to this very, what your system has to do. And if you had to guess which of the 4 receptors are being used here. So this is a test of your memory or your quality of your notes. Huh? No, Merkel, because it's high spatial resolution. Because you're moving the finger, so you don't have to worry about the fast part. So that it's the Merkel receptors which have the highest spatial resolution. But everything is being activated and the brain interprets. Okay, so this is active, right? You're moving your finger in a program, and we do that. The same is true for visual reading. We also and there's more here about which I don't know how much how well studied this area is, because in visual normally when we read, we do not actually read every letter. We read. I looked into this some years ago. We look 40% of the way into the letter because we have foveation. I mean, here there is a fovea, which is your finger, but for the human reader also there's a fovea, and you want to put the fovea not at the first letter of the word, but 40% of the way in, because that way you get enough letters that you can guess the word and then you move on. So we do not actually painstakingly get every character. We get enough to guess and then we move on. And as you know from the success of LLMs, there's a lot of redundancy in English. And as you have learned, as you become good readers, you read fast because you have your cognitive system is guiding that. Somebody had a question. Yeah.
So it looked like in the video they're like kind of rubbing. It's not just like touch.
Yeah.
It's like
sliding. I thought of it as more as sliding. Yeah.
Make it like super resolution that way by like integrating across time and getting you can get on like the boundaries of your different like receptors and things like this, or like do they know why this is useful to people?
Honestly, I don't know. I've not my knowledge of Braille is what like this video captures my knowledge of Braille. I read a little bit more about the history of Braille because that was interesting. And there would presumably have been some, I mean, what I would look for are papers in this business from some psychologists trying to analyze this. And you would have to do controlled experiments, but I just don't know the literature well enough. Okay, okay, here. Here is a paper, this is an old paper from Lederman and Klatsky. This, I think I gave you a few examples. I gave you the example of reading, where there is a procedure being followed. I gave you the example of weighing an object where there's a procedure being followed. So Lederman and Klatsky, what they tried to do was they gave people many different tasks. And then from that, they tried to abstract if there was a common set of procedures which were being used. And this is their list. So the first one is this lateral motion, which is if I ask you to judge the texture, is it like rough paper or smooth paper? So what you do is you just move your fingers on the surface. Okay, unsupported holding weight. Okay, I think we already talked about that, moving the hand up and down. Pressure, what would you do if you asked you whether it was hard or soft? You press your finger down on it, right? Or multiple fingers down on the object. Enclosure, volume, you would just, so think of all these experiments being done in the without vision. You can do these experiments with the eyes shut, right? Okay, you can guess the volume. Static contact temperature. So yeah, so that's easy. You're activating the temperature. By the way, this is quite helpful and for an interesting reason. Why does if you have a piece of aluminum versus a piece of wood, why does the aluminum feel colder?
It's a conductor.
Because it's a conductor. So the heat is conducted away, so it feels colder. So so in a way, it's just a proxy to sort of heat conductivity, which is correlated also to electrical conductivity. Contour following, so this is like instead of volume, you go around the boundary of the object. I mean, I wouldn't take this literally as, okay, these are the 6 and there'll be variants, it could be 8, but the important idea here is that there are policies being followed which are just for getting good perception. You're trying to answer perceptual questions. What's the weight of the object? Is it a hard object? Is it a smooth surface? And you execute a procedure, hence exploratory procedure. Yeah. I mean, we are primates. Probably, I don't know the answer to whether somebody has done that experiment, but my guess would be yes, because the touch systems are very similar. These are not different. Okay. Okay, so I think I've covered. So so these two, the two on the left were really the hand as a sensing device. So the hand is like a camera based on touch, if you will, touch and proprioception. Because when you are moving that object in your palm up and down, you're also getting force measurements and so forth from the sensors in your the musculoskeletal system, right? The muscle spindles and in the Golgi tendon organs and so on, they are also being activated. And now let's turn to the action side, which is now the hand as something which acts in the world. And we can distinguish between what are called prehensile movements and non-prehensile movements. And prehensile refers to grasping, basically. Prehensile, the word just means grasping. And there's a classic paper on this from Napier in 1956. Actually, there was someone called Schlesinger in Germany who wrote some papers in the 20s on this. But somehow Napier's classification is the one which caught on. And you can, in fact, whenever there's a classification or category taxonomy, you can choose how deep to go. But the highest level is this distinction between a power grip and a precision grip, power grasp or precision grasp. With the power grasp, you can see what that is, right? That's where you apply a lot of force. And then there is precision grip where between the thumb and the forefinger. Okay. And in children, which of these do you think develops first? Power grip, right? So because they once they start to be able to open their hand, they are able to do this. And I think of it as if you did principal component analysis, suppose you had tons and tons of photos of people doing grasping movements in the real world, or even just movements involving the hands. And then you try to find the first principal component. What's the most commonly used degree of freedom? It's going to be this one, okay? And this actually accounts for the success of parallel jaw grippers. So parallel jaw grippers that people in robotics use, and I hate, because in my view, those are, I mean, we want to get to dexterous manipulation, and parallel jaw grippers is like, it should be like 20th century, not 21st century. But parallel jaw grippers capture the most common degree of freedom that you want with your hands, which is this movement, right? The power grasp. Okay. But we want to do a lot more subtle stuff. That's why we want to use multi-finger hands and so on. Okay. This list is by no means exhaustive. There is a book that I have. It's I'm showing it here, but for the people in Zoom, they can just see that. So this is from someone called Noriko Kamakura. And I think of her as like having done the best work in this area of understanding the movements of the hand. And sadly, all this work was in Japanese and not known to people in the West, who came up with their own various hierarchies of grasps and so on, which are all actually inferior to the work that she did like in the 70s and 80s. Okay. But anyway, this work has been translated in English and is now available. So what she did was a very careful study of how we use our hands in daily life. So I worked on this project called Ego 4D. So she did like that Ego 4D kind of thinking, except she was doing it in the 70s. What she did was she made a list of what are common objects and what are common verbs corresponding to common actions. And then she brought people in the lab and she had this list of, okay, these are the common objects and these are the common actions. And then she had a way of identifying what parts of the hand are touching the object. Very simple. Just put some ink on the object. And then when you hold the object, then your fingers will have the ink. And now you have recorded what parts were in contact. So anyway, I'm not sure if I believe in the strict taxonomy, but the value of the taxonomy is to show the variety of ways in which we use our hands. And we don't use our hands just one hand at a time. We use bimanual. We use multiple hands at the same time.
The idea is like the apples, there is only one way to grasp the apple, for example, for one particular object, or?
No, it depends on what you want to do with it. So my canonical example for this is a coffee mug. Okay, there's a coffee mug when I am drinking from it. There's a way I hold the coffee mug when I want to hand it to you. There's a way I hold a coffee mug when I want to put it into a dishwasher. There's a way I hold the coffee mug when I take it out of the dishwasher and I want to put it in my cabinet. All of these are different. It's the same damn coffee mug, right? So grasps are always functional and therefore they can vary. And again, yeah. Okay, now to end the lecture, I think I'm within 4 minutes. So, okay, therefore that's great. And now I want to talk about, so this is what we talked about, how we use the hands for manipulating objects. So, and I've chosen not to go into too much detail here because basically we're going to do later in the class the use of dexterous hands for various kinds of manipulation tasks. So now I want to end in the last 3-4 minutes of this class with how we use our hands, not necessarily just for manipulation, which is for communication. And there are theories which say that, in fact, the communication with gesture might have been the prelude to language. Okay, so conversational gesture. So these are slides from some old project that Shiri and I and a few others were involved in. But I have videos from this which are fun to watch. So the first thing to note is that how we use our gestures accompanying language is actually of different types. There is sign language, which is a full-fledged language. Okay, it has a grammar, it's a syntax, it's like spoken language. Okay, and then you have gesture which accompanies speech. So when I'm talking, I cannot but emit. I can't help it. I'm moving. My hands are moving in line with this. Then there is what is called Italianate gesture, which I think is self-explanatory, but I will give you a video. So first, let's talk about sign language.
Mandela taught us the power of action, but he also taught us the power of ideas.
Okay, so that's sign language. So there's somebody who's interpreting. So there is his English speech, and then there is the equivalent of that in sign language, which is, so I think here the fun problems are, when will we give robots the ability to speak in sign language? Okay, we should be able to do it. Okay, there are some papers to be written here. Okay, and then I will end my lecture I will end with Italianate gesture.
What? Come on. Full of people.
I thought there was more in there. Okay, anyway, you can find more on this on the web. But at this, thank you very much.